Welcome. In Chapter 2, you will be learning about mapping GIS data. Geographic information systems are used for many purposes, but creating maps is one of the most common. The practice of cartography or map making has a long history. And in this chapter, you will begin to understand the basic principles behind portraying spatial data and the aesthetic challenges in designing an effective and attractive way to communicate ideas through maps. Cartographers may choose a variety of strategies for symbolizing features in a map. When creating maps, it is important to distinguish among nominal, categorical, and numerical data because the type of data will influence the kind of map that can be made. Nominal data names or uniquely identifies objects in a map. For example, state names, owners of parcels, tax ID numbers, or even parcel ID numbers. Each feature in the map is likely to have its own value and is usually portrayed on a map with labels. Single symbol maps are typically chosen to display nominal data, which combines with labels. This will display all features with the same symbol on the map. Categorical data separates features into distinct groups or classes. It places features into defined number of distinct categories, which is shown below as wells by type, road classes, or land use. Here those category names are in text, but they can also be represented as numeric. When mapping categorical data, they are portrayed by different symbols for each category, and therefore are represented by what we call a unique values map, which gives each category a different symbol. Here are 3 different examples of unique values maps where different symbols for each category or value are represented on the map. The first map shows volcano types, each represented by a different symbol. Road types you can see in the second figure, and each of the road types is shown by a different color. And geologic units as well, each is shown with a different color, each representing a different value or a different category. Ordinal data have categories that are ranked based on some quantitative measure, although the measure may not be linear. For example, cities might be classified as small, medium, or large, and students can be assigned grades of A, B, C, D, or F. Numeric ordinal data may be represented either with unique values maps or graduated color maps, but ordinal data must be represented by unique value maps if the values are text, but the colors should be the same shade and give a sense of ink, as shown in the figure on this slide. Numeric data represent phenomena that fall along a regularly spaced measurement scale, such as distance or rainfall. Interval and ratio data are both types of numeric data. Interval data have a regular scale but are not related to a meaningful 0 point. Temperature data, measured in the familiar Celsius or Fahrenheit scales, are interval data because a temperature of 0 does not correspond to a complete lack of temperature. Any scale that can have negative values, such as elevation, is an interval scale. Interval scales support only addition and subtraction. The difference between interval data and ratio data is that ratio data have the added property that the measurements have a meaningful 0 point that indicates the absence of the thing being measured. Precipitation is an example of ratio data. 0 precipitation corresponds to a total lack of rain, and 2 inches of rain is twice as much as 1 inch. Ratio data supports all 4 arithmetic operations of addition, subtraction, multiplication, and division. When determining which symbology should be used for creating a map, you must first identify which type of data set you have: nominal, categorical, ordinal, or ratio interval data. This review slide will help you to identify which choice to make in symbology for creating your map. As a review, nominal data, you will create a single symbol map. Categorical data, you will use a unique values map. For ordinal data, it will be determined whether you have non-numeric or numeric data. For non-numeric data, you will use a unique values map, and for numeric data, you will use a graduated colors map. For ratio and interval data, you will be able to choose between graduated color for polygons, graduated symbol for points and lines, dot density, and chart maps. When mapping numeric data, interval and ratio data must be divided into classes before mapping. When mapped, you can use variations in symbol size, thickness, or hue. This slide shows two examples of classed maps. On the left is a graduated color map, also known as a chloropleth map. The population for 1990 per square miles has been divided into 5 classes. In this map, the darkest colors represent the greatest population density per unit area, whereas the lightest color indicates the smallest population density per unit area. On the right, population has been demonstrated using a graduated symbols map, whereas the largest symbol represents the greatest population density, and the smallest symbols represent the smallest population density. When choosing colors for chloropleth maps, it is generally best to use a color scheme that changes in saturation very generally, or where close hues are used to indicate an increase, such as the monochromatic blues. Avoid using too many colors, which tend to make it difficult to interpret where the highest values are represented and where the lowest values are represented. For some attributes, the size of the feature influences the value of the attribute reported for that feature. For example, counties with larger areas tend to have more acres of farmland or larger populations. Such data should be normalized to the quantity per unit area when they are mapped, in order to prevent the size of the measurement unit from influencing the map appearance. Therefore, population data are usually normalized to show the number of people per unit area, which is the population density. Another way to normalize values to the area of a polygon is to create a dot density map, which uses randomly placed dots to show the magnitude of a value in the attribute table. Each dot represents a certain number. In this figure, 1 dot equals 100,000 people. Note that the location of the dots, which are randomly placed, do not necessarily represent the actual distribution of people in the state. Chart maps allow you to expand the number of attributes that can be displayed on a map by replacing a single symbol with a chart representing several attributes. The chart can be a pie chart, bar chart, or a stacked bar chart. Rasters can also be displayed in maps. Rasters are a cell-based data model in which an array of cells or pixels store numeric values relating to some feature or quantity on the Earth's surface. Rasters are broadly grouped into 3 main types, each of which is displayed differently. The first is thematic rasters, the second, image rasters, and the third, indexed rasters. A thematic raster represents map features or quantities, such as roads, geology, elevation, or vegetation density. When rasters are used to store objects, such as roads or land use polygons, they are called discrete rasters and appear like the top figure on this slide. Typically, they are created by converting features from a vector data set to a raster format. Discrete rasters contain groups of adjacent cells with the same value. In contrast, continuous rasters store values that represent a continuously varying quantity, such as elevation, shown in the bottom figure on this slide. The methods used to display thematic rasters are similar to those used for displaying vector data and depend on the data type. A raster representing categorical or ordinal data is displayed using a unique values map. Just like the unique values map used for feature classes, each value of the raster receives its own color, just like the land use map, which is the top figure in this slide. Color schemes for unique values maps have 32 possible values and work best with data that have relatively few categories. When representing ordinal data, a monochromatic color scheme is used to communicate a sense of increase. The bottom figure in this slide shows a thematic raster containing interval or ratio data, which must be classified into ranges in one of two ways. The classified display methods divides the values into a small number of bins similar to a graduated color map. A color ramp is chosen to assign the colors to each bin. The elevation map in this slide has 12 classes represented by 12 colors from a color ramp. The stretched display method scales the image values to a color ramp with 256 shades. The raster is first subjected to a slice, which rescales the elevation value ranging from 800 to 600 meters into a 256 bins, then matches the bins to the 256 shades in the color ramp. This slide shows how you can display thematic rasters based on the information provided in the previous slide. On the left, again, you'll see categorical or ordinal data, and you have unique values showing discrete color. On the right is an example of the interval ratio data showing classified and stretched. This slide shows how slicing rescales the elevation values into 256 bins and then matches the bins to the 256 shades in the color ramp. This slide shows how after slicing, stretching enhances the display by removing less common values at the tail or the tail ends, which gives you a so-called standard deviation stretch. Basically, it scales the image values to a color ramp with 256 shades. Image rasters include aerial photography and satellite data. The pixels represent degrees of brightness caused by light reflecting from materials on the surface. The brightness values are often placed on a scale of 0 to 255 digital numbers. A dark shadow would have a low brightness and a low digital number, whereas a white cement road would have a high brightness and a high digital number. An image raster may contain one or more bands of information. The image on the left of this slide shows a single band image, and the example on the right side of this slide shows a 3-band composite image, the RGB or red, green, blue band composite. The single band image represents a black and white photograph. The 3-band composite image represents a color image. Many satellites and airborne cameras measure brightness in more than 3 wavelengths and produce more than 3 bands. Landsat images, for example, have 7 bands. Stretching maximizes brightness and contrast, and images usually contain a 0 to 255 range values, but they may not utilize the full range. Since the image, once it's stretched, has few values near 0 or 255 because the tails are taken out, most of those pixels will occur in the middle gray range. This slide demonstrates how the stretched display method can improve the display of normally distributed values by ignoring the tails of the distribution. The image on the left shows no stretch at all. The middle image shows a minimum-maximum stretch, which is a method that assigns the lowest and highest image values to 0 and 255 respectively, and stretches the remaining colors along the ramp. An even greater contrast can be developed using a standard deviation stretch, as shown in the figure on the right, which uses only the values within 2 standard deviations of the mean. This slide shows different display methods for rasters. On the left, you have true color, where the 3 to 2, 1 red, green, blue ratio is applied. False color, which is a 4 to 3 to 1 application, and then Landsat, which has a 7 to 4 to 1 band image. A USGS topographic map is an example of an indexed color raster. Since the RGB color model uses large amounts of memory, an alternate method for storing color identifies a restricted set of colors that actually appear in the image. It assigns an integer from 0 to 255 to each color and stores the RGB proportions needed to make it. The list of colors is called the color map and is stored with the image. Each value in the raster is portrayed using its assigned color, as shown on the left. On this USGS map, the parks are represented by pixels with the value 5 and are displayed using the assigned green color. Mapping numeric data, raster or vector, requires classifying a range of values into a small number of groups, each of which can be represented by a different color or symbol size. This process is called classification. There are many ways to classify data, and the choice of the method affects the appearance of the map and the message that it portrays to the viewer. Data can be distributed in different ways. It can be normally distributed, uniformly distributed, skewed, or distributed in a bimodal fashion. Understanding how your data is distributed will help you in determining which classification will best suit your data. One classification option is known as the Jenks method or Jenks natural breaks. This method sets the class breaks at naturally occurring gaps between groups of data. Each class interval can have its own width, and a number of features in each class will vary. The Jenks method works well on unevenly distributed data and works well with almost any data set, making it a natural choice for the default classification scheme in ArcMap. The equal interval classification divides the values into a specified number of classes of equal size. This method is useful for ratio data, such as income or precipitation, because it gives a sense of regularity to the observed increases. However, it is hard to predict how many features will end up in each class. Notice in this farm size example that nearly all of the states fall into the first class. A defined interval classification is similar to an equal interval one, except that the user specifies the size of the class interval and the number of classes then depends on the range of values. This method will create rounded values in the classes that are easy to interpret. Defined interval maps are ideal when comparing classes composed of percentages, dollars, temperatures, and other values when specific break values are desired. It does suffer the same disadvantages, though, as the equal interval classification. A quantile classification puts about the same number of features in each class. This method will create a very balanced map with all classes equally well represented, but some of the features in the same class could have very different values, and features in different classes could have similar values. Quantile classifications are best applied to linearly distributed data. If you go back and compare this map with the previously maps shown using the different classification systems, you'll notice that the quantile classification highlights differences between the eastern states that are hidden in the Jenks equal interval and defined interval classification maps. A geometrical interval classification bases the class intervals on a geometric series in which each class is multiplied by a constant coefficient to produce the next higher class. A geometric interval classification is designed to work well with continuous data like precipitation and to provide about the same number of values in each class range. It works especially well with positively skewed data distributions. A standard deviation classification apportions the values based on the statistics of the field. The user selects the class breaks as the number of standard deviations, and the data range determines the number of classes needed. This method excels at highlighting which values are typical and which are outliers. The map on this slide shows the yellow states are close to the mean farm size. Several eastern states appear to have smaller than average farms, and some western states have much larger farms than average. This map is best applied to normally distributed data. This classification summary slide should be helpful when trying to determine how to classify your data sets to produce your maps. It is important for all users to understand a little bit about ArcGIS and map documents. The ArcMap program has two main functions. First, it provides a place in which data sets may be viewed together and analyzed. Second, it is used to develop a map layout, or a map page designed for printing. ArcMap creates map documents, a collection of spatial data layers and tables and their properties, and it also stores a map layout intended for printing. This slide shows an example of the map document. When a feature class or a raster is added to ArcMap, it becomes a layer. This distinction is important. A feature class is a stored set of spatial data, but a layer points to a feature class and stores information about how to display it and use it. The same feature class can be accessed by multiple layers to present different views of the same data, even within a single map document. Layers are held in memory and stored when the map document is saved. The information in the layer, such as which symbols should be used and whether the features have labels, are called the layer properties. Creating a map involves manipulating these properties in menus to produce the desired result. Map documents organize layers using data frames, which are windows that contain groups of layers that are drawn together. Maps can contain multiple data frames. One frame at a time is designated the active frame, and then all commands and actions, such as adding layers or creating a scale bar, occur in the active frame. To add data to frames, you must first connect to a folder where the data is stored. Once you add the data, the layout view contains the map part of the page, and it can have multiple data frames to have different maps on one page. It also contains the layers that make up the maps that you are working with. On this slide, you can see in the table of contents that there are two data frames, one labeled geography and one labeled population. In the geography data frame, there are multiple layers: volcano type, airports, volcano elevation, rivers, etc. And in the population data frame, cities, median age, and some other demographics. You can see that the active frame is the one on the top. In order to get to the data frame properties, you must right-click on the data frame in the table of contents, and that will bring up the data frame properties menu box. Notice the different tabs in the data frame properties box. It is very important to understand that a map document does not store the GIS data files within it. Instead, the map stores the name and the location of the spatial data, known as its source. Most changes to the map document do not affect the source data, only its properties within the document. And some functions do change the source data, such as adding attributes or editing boundaries. Because the source data are stored outside the map document, changes to source data affect all map documents using the same data set. Map documents keep track of the source files by storing the location of each file as a path name, which lists the successive folders traversed to a data set, each separated by backslashes. The path name C, GIS Data, USA, States, Shape refers to the feature class States shapefile, which resides in the USA folder, which in turn resides in the GIS Data folder, which is found on the C drive. It is very important for you to understand path names so that you always know where you have stored your data set and your map information. The path name just described in the previous slide is termed an absolute path name because it starts at the drive letter and proceeds downward to the file. When searching for a file using an absolute path name, the search begins at the drive level. A relative path name is used to indicate that search should begin in the folder containing the map document. A double dot indicates movement up one folder. So the relative path name shown on this slide indicates a search up one folder and then down into the USA folder and then to the States feature class. Map documents can store either absolute or relative path names chosen by the user. When a map document is opened, it searches for the states starting at the C drive down through C, GIS Data, USA, State Shapefile in order to locate and draw the states in the map. If you are working on a computer and save your map files to a stick or an external hard drive, you will be breaking the links for where your files have been saved. The path no longer exists in the C drive, it will exist in the drive that your external or stick has been saved in, usually D, E, F, or G drive. When your links are broken, the layer will appear with a red exclamation point, and the user can manually locate the data to fix the links. But this can be time-consuming, and our catalog can fix multiple links efficiently. The best solution is to direct the map documents to store relative path names. In this case, the state's path name is stored as .USA states shapefile, and it no longer matters whether the GIS data folder exists on the C drive or E drive or K drive. As long as the relative positions of the map documents and USA folders remain the same, the map document can always locate the data. One of the most important things to remember is that path names, including the names of map documents and spatial data sets, should not contain spaces or special characters such as hash signs, @ and so on. Use the underscore character to create spaces in names if necessary. Although ArcCatalog and ArcMap allow spaces in names, spaces create problems for certain functions. It is wise to avoid them. In summary, broken data links occur when a map document cannot find data using the stored path name because either the data were moved or deleted, the drive is not available, map documents copied to a different computer, or data was not sent with the map.